Hey, my name is Rakeen, and today is March 23rd, and I will be demonstrating my 2ei4 project. Okay, so let's just get right into this. This is the circuit schematic over here, and what I've done is I've used a common collector topology. Now, the reason I've done that is because it has really high input impedance but very low output impedance, and this means that it doesn't draw too much current. In addition, I went ahead and used the transistor that I used is a BJT, and I use the NPN because it has really good linearity and it doesn't struggle with switching voltages, like turning off and on really quickly, which is good for the frequency that we're going to use. We're going to use really high frequency, which I think is kind of necessary for this. Now, these resistance values I will explain further in the calculation, which is down here. So I went ahead and did AC analysis first, and I was able to get these certain resistances. I'll start with a DC analysis though, just because it's a little bit simpler and it'll make sense later on. Now, when you have a configuration like this, you can go ahead and use Thevenin's to convert it into this kind of situation. Now, all I went ahead and did is I assumed a 5 volts and -5 right here and then checked. And I was able to conclude that this is in fact in forward active mode. Now, here is the small signal analysis that I did to get the resistance values. This is a dumbed down version of the circuit, which I used because I assumed that the voltage coming in is going to be relatively close to the voltage going out. Now, this isn't necessarily true, but I went ahead and did this just because I wanted to go ahead and do the transconductance calculation. And for the transconductance, you just simply need a range of the input voltage, which is in this case the voltage in the gate, the voltage at the base. Now, the voltage at the base will have the highest it can ever have in terms of fluctuations is a max of 0.5, and that's just because of the voltage being fed in. Now, because of voltage division, it will actually have less than this, but it's just safer to go ahead and use 0.5. So using that and substituting our relative values like the load resistance and the thermal voltages, we're able to get a transconductance of greater than or equal to 0.99. So now we can return back to the original circuit and do analysis again. Here we're actually going to have to use voltage division, and we can use voltage division because the current being drawn from this is going to be, we can assume 0. So using voltage division, you're able to go ahead and you can go ahead and find a different value for the input and output, so the actual gain. Now what you have is you have a gain from here to here that is relative to the transconductance, which we calculated earlier, and the parallel resistances. Once you keep converting and doing the math, what you'll have an inequality of the parallel resistances, and we can evaluate each inequality. We can see that the first evaluation right here just means that the resistances that are in parallel have to be greater than or equal to 1K. Now, this inequality is always going to be true, and that's just going to be the case as long as you have positive resistance values. I went ahead and used a 10K resistor because in parallel they're equal to 5K, which is greater than 1K, and additionally there's an abundance of them in the component kits. Now, once I knew that I used 10K, I went ahead and plugged it back in to get the gain, and I had a gain of 0.97. Okay, so now let's get into the simulation. So right here, the transistor that I'm using, the BJT that I'm using, is actually the same as the component. So this is the same transistor that I'm using in the breadboard, which is the 2n3904. Now, we'll start with the analysis. Before I do any of that, I just want to explain why I'm using these capacitors. Now, the reason the capacitors are there is simply to act as a high-pass filter, which just allows high frequencies to pass through, and it kind of segregates the DC voltage and the AC voltage. Now, addition to that, we'll just go ahead and start with the transient analysis. Because I'm using such a high frequency in the actual circuit, I'm using slightly a lower frequency, but I can definitely show you with higher frequencies as well. The circuit works better with higher frequencies, as then the capacitors really shine and they're able to really let the AC current through while not letting the DC through. Additionally, this resistance isn't part of the actual circuit, but I'm adding it here just to reference it to ground, so that when I'm measuring it, it centers it to ground instead of having a voltage offset, which it normally does. Now we can do the transient analysis. Now this is what it looks like. Let me show you again. So this is the input voltage. I'll just be a little bit more thorough. What I'm labeling is I'm starting at, I want to say 0.1 milliseconds and measuring up to 0.2 milliseconds. Now, the reason I'm doing that is I'm just giving the circuit a little bit of time to stabilize and then doing my measurement. And the reason I'm measuring at such low periods is because of the high frequency. That period is enough for a couple of actual sinusoidal, that time interval is enough for a couple of like sinusoidal periods. So as we can see, that's the voltage in, and we can measure the voltage out and that looks like a perfect replica. Yep, and we can actually zoom in to get our voltage gain. As we can see, it's very similar, but there is a slight gain that is less than 1, and we can do our calculations. So as we can see, we're feeding a 500 millivolts in, and we're getting around 476 millivolts. So we can use our calculator to get the value, the gain value. So 476 divided by 500. And we're having a gain of roughly around 0.95, which is very similar to what we calculated in our a small circuit, which is roughly the same as what we calculated in our small signal analysis. Now, in addition to that, we can do a couple of other analyses. We'll go ahead and do an AC analysis. We'll convert this to an AC voltage, and yeah, this doesn't matter. We'll have that as AC. Let's just get rid of this. Okay, and we'll change this over to do AC. Now this just lets us know what range the circuit works best for in terms of different frequencies. So that's our reference, and as we can see, this is our V out. Okay, so what this tells us is that for low frequencies, this circuit doesn't do justice generally, like it's not very good, and that makes sense as the capacitors work better for high frequency signals. Now, as we increase the frequency, what we start seeing is that the output voltage matches relatively similar to the input voltage. And the offset also matches what we would expect the offset to be for the input voltage. So this shows you that the amplifier works really good for high frequency AC signals. Now we can also do a DC analysis. We'll start with a DC Swift. We'll start with a DC of 0 and then do our analysis. Sorry. Okay. Now, before we even start, we should be able to say that there's going to be nothing on the output voltage, and that's because we've established that this circuit is the best. Because of the capacitance, this circuit is the best for high frequency AC signals. We'll go ahead and do a simulation. Now, this is the voltage in and the voltage out is 0, and that makes sense. This circuit isn't meant for DC voltages. So we'll get right into the real circuit. We have the 83 feeding into the actual breadboard. This supplies our voltages, acts as our waveform, and does all the measurements. Right here we have the 2ei4Project3, our transistor. We have at the very left the emitter, then we have the base, and then the collector. As you can see, the collector feeds right into VDD, and the base is fed into our parallel resistors over here, the resistors that connect to VDD and VEE. Now, the emitter is fed onto this capacitor, which we take measurements from. This filters out our DC, and then the resistor connects it to VEE. Now, in addition to that, the input voltage over here goes through our 100 ohm resistor. It then goes through the capacitor, which filters out. It pretty much just prevents AC going back through. DC going back through allows the AC to then change the voltage right here at the center that is shared between these two resistors. These resistors are both 100K resistors. Everything else is equal to the load and supply resistances. So that's 100 ohms, that's 100 ohms, and these are our 100 nanofarad capacitors. I used non-polarized capacitors because I felt like it makes the most sense for AC circuits. And we can see that, and we'll go right into the actual measurements. Okay, so here's the wave gen, and what we're doing is first we're supplying a 5 volt and negative 5 volt for VDD and VEE. Now we have a wave gen with 1 kilohertz frequency, an amplitude of 500 millivolts, which is 0.5 volts. Now if we take a look at the scope, what we see is we actually see fairly good linearity, and we see that the voltage is pretty much preserved from the input. We can also go ahead and do some measurements to actually see what the gain is. However, before we do that, we also discussed that higher frequencies are better, so we will move this up to, let's try 10 kilohertz. Now, if we take a measurement at the scope, what we can see is, I'm just going to change this range over here to something like that. Okay, we can see practically perfect linearity, right? It matches up quite exactly. And the higher we have the frequency, the more like perfect gain that you'll see, like a gain of 1. In addition, we can, now let's actually just take the wave gen and take it back down to 1 kilohertz. Now that's okay, but well, we should lose it, yeah. So as you can see, there is a slight offset. Now, if we go to the spectrum, what we can see is it also demonstrates generally good linearity. So I just let it run for a little bit, and the reason I say that is because we can see that that channel 2, which maps the input voltage, channel 1 follows, with channel 1 being the output voltage, follows the input voltage quite similarly, right? So as the input voltage decreases, channel 1 decreases, and as the output voltage, as the input voltage increases, channel 1 also increases. So you can see the map right here, which is a really good indicator that our circuit does work as intended. For different frequencies, we have generally a very similar wave that's running.